Hello everyone, this is Dr. Webb. In this video we're going to be looking at local maxima and minima in multiple directions, mostly in two variables. And so I think for this topic it really helps to go back and look at how we originally did this in one variable in Calc 1, and then think about how the definitions need to be shifted to work in a higher number of variable framework. So, going back to Calc 1, this is the definition for local maximum. So you say a function f has a local maximum at x naught if we have some interval a to b. And so let's draw a little picture of what's going on here. So there's x naught, and then we have some interval from a to b, and such that if we pick any c also in that interval, then the value of the function at x naught is at least as big as the value of the function at c. And so let's draw our function, somewhat in blue. And so there's the function value at x naught, and you can see that it's higher than it is at c. And so that's the idea of the local maximum, is that you're kind of taking some distance around x naught, and that's giving you this interval from a to b. So if we're doing this in higher dimensions, well, now we're talking about some point x naught, y naught. Well, if we want to think about the region around that point, it's not just some straight lines going through there. We actually have to kind of take a whole little ball around that point, right? And so rather than thinking about intervals, it's sort of more natural to think about something like, say, circles around that point. So that's how we'll shift the definition. So for a two-variable function f, we'll say it has a local maximum at x naught, y naught. If we can take some radius around that point, such that for any a comma b that's within that radius, and so you see here we have the distance function measuring how far ab is to x naught, y naught, then that means that the function value at x naught is going to be at least as big as the function value at ab. And so if we're trying to draw this out, a little bit of space that we have here, so here's x naught, y naught. Let's draw a little circle around it. That's going to be radius r. Say the point AB is right there. Well, then sort of that region over that, the point coming from x naught, y naught is going to be up higher than any other point, just looking above that circle. And so here we focused on the definitions of maximums and minimums, of maximums here. What do we need to do if we wanted to, say, shift this to talking about local mins, local minimums? Well, we can change this definition from maximum to minimum just by changing the inequalities at the end. If f of x naught is less than f of c for all c, then f of x naught's a minimum, and so if on this circle f of x naught, y naught was less than or equal to every other point in there, then this would make it a minimum. Okay, so how in Calc 1 did we look for these local maxima and minima? And if you remember, it was tied into finding these critical points. All the local maxima and minima had to occur at critical points. And so in one variable, what was a critical point? Well, a critical point happened where either you couldn't take the derivative of the function. So either it was, if it was continuous, that meant that there was some sort of cusp there where you couldn't measure it, or the derivative of the function was 0. And so that's saying that the tangent line is horizontal. So saying the derivative is equal to 0 is the same thing as saying the tangent line is horizontal. So how would we adjust that now if we're thinking about things in higher variables? Well, so we still need to put in that the critical points could, these maxes and mins can happen at places where f isn't differentiable. There still is the same idea of having sort of a cusp. You can sort of think about sort of the point of a top of a cone. If you have an inverted cone, that would be a cusp. You don't really have continuous derivatives all around there. So what about adjusting what would be appropriate to look at instead of the derivative, because we have more than one derivative equaling 0? Well, it turns out that the natural thing to look at is the gradient. And so if the gradient of the function is the 0 vector, because remember gradient gives you a 0, then that's going to be a critical point. And so what this means for the gradient to be equal to 0, if we're doing this in, say, 2 variables, well, this means that both first partials are equal to 0 there. It also means that, we talked in the last video about directional derivatives, and the directional derivative would be the gradient dotted with a unit vector in that direction. But if the gradient is a 0 vector, that means all the directional derivatives are 0. So du of f is equal to 0 for all unit vectors u. And what that also means is that since the value of these partials get tied into the normal vector to the tangent plane, if both of those are equal to 0, that means that the normal for the tangent plane is going to look like 0, 0, minus 1. And so if it's 0, 0, minus 1, that means that the normal is pointing straight down. And so if it's pointing straight down, the plane is perpendicular to it. So the tangent plane is horizontal. And so this idea of having the tangent be horizontal is exactly the same as what we saw in one dimension. It's just that now, instead of having a tangent line, we have a tangent plane. Okay, so here's a multivariable function, x cubed minus 4xy plus 3y squared. Let's find the critical points for this. So we're looking for where the gradient is equal to 0, 0. And so this is talking about partial in terms of x. This is talking about the partial in terms of y. So we got to get these two partials. So what's the partial in terms of x here? Well, derivative of 3x squared of x cubed is 3x squared, getting ahead of myself, minus the derivative of 4xy in terms of x is going to be 4y, and then 3y squared, that doesn't have any x's in it, so that just disappears. Partial in terms of y, x cubed doesn't have any y's, so it disappears. Minus 4x coming from minus 4xy, and then 3y squared turns into 6y. Okay, so we've got our two partials here. We want to find where these are equal to 0 simultaneously. Okay. And so we're solving for the x and y values that make both of these partial derivatives equal to 0. So I think it's easiest to deal with the bottom one first. So this one, if we set it equal to 0, that's saying that 6y has to equal 4x. So y would have to be 2/3 x. And so then if we then go and plug that back into the partial for x, we're going to get 3x squared minus 4 times 2/3 x is equal to 0. So we have 3x squared minus 8/3 x equal to 0. And so looking at this, both terms have an x in them, but that x is important here because that's saying x equals 0 is a root of this. So we don't want to just divide by x, we want to keep that in there. So we will factor out the x, and we'll be left with 3x minus 8/3 equal to 0. And so out of this, we get one point being x is equal to 0, and the other point coming from here, if I do 3x is equal to 8/3, then x is going to be equal to 8/9. And then to get the y values, plug this back into where we solve for y there. So 2/3 times 0 is 0. 2/3 times 8/9 is going to be 16/27. So our two critical points here is at the point, our two critical points, they're at the point 0, 0, and at the point 8/9, 16/27. Okay, so that's how we find the critical points. Now, once we have the critical points, how then do we identify whether these points are maxes or mins? Okay, and so one way we did this in Calc 1 is using the second derivative test. And so if we take a critical point, or a point where the derivative is equal to 0, we need the derivative, we need it to be differentiable to be able to take a second derivative. So if it's a critical point and we're using the second derivative test, we can assume that the first derivative is equal to 0. Well, if the first derivative is equal to 0 and the second derivative is negative, well, if the second derivative is negative, that means that it is concave down. And so what's happening at x0? If it's concave down at x0, then that's going to be a local max. On the other hand, if it's concave up at x0, then that's going to be a local min. And so we use the second derivatives, you can use the second derivatives to figure out whether you had a max or a min. So how does this change in, say, 2 dimensions? Well, we have more than one, we have more than one second order partial. In fact, we have 3 of them. So is there a way to use them? And the answer is yes. And so this is a second derivative. This is really a second partial derivative test for f of xy. And so here we need the gradient to be equal to 0, like when we were looking for critical points. And then to incorporate the information from the second partials, we're going to look at this value d. And what d is we take 2 partials in terms of x times 2 partials in terms of y, and then we subtract off the mixed partials squared. We're going to call that d. And that d is going to kind of be playing the role of f double prime of x0 that we saw for one variable. And so if d is positive, and if d is positive here, so if we're looking at this d, it's f of xx times f of yy minus f of xy squared. Well, since we're subtracting f of xy squared, this part of it right here, because we're squaring it, that makes it positive, but then we're subtracting it off. That part has to be less than 0. Right? And so the only possible way to get d to be greater than 0, well then these two partials, fxx and fyy, have to have the same sign, and their product has to be bigger than f of xy squared. And so that's what's happening if d is bigger than 0. So if d is bigger than 0, but fxx is negative, so if this is less than 0, this is always going to be negative. The only possible way for this to be bigger than 0 is if fyy is also going to have to be negative. So if fxx is less than 0, then that automatically means that fyy is less than 0. And so then you can think about, in both of those directions, the curve is concave down. And so if the curve is concave down overall, then again, that's going to correspond to a local max. So local max, you take this d, if d is positive, and both of these partials, fxx and fyy, are negative, then that's a local max. If d is positive, but f of x is also positive, and so that also means that f of yy is positive. So they're both kind of concave up at this point. And so if they're both concave up, that's going to be a local min. Okay. But in 2 dimensions, we can actually get something else happening other than just a max or a min. And that's what's called a saddle point. And a saddle point happens whenever this d is negative. Okay. And so how can this d be negative? Well, one way that this d could be negative, so this part is always, again, this part is always going to be less than or equal to 0. And so one way that this could be negative is if, say, f of xx was positive, but f of yy was negative. So everything in here was negative, right? And so if you think, something, the graph of that, if f of xx is positive, but f of yy is negative, well, then what that means is that in sort of the x direction, it's concave up, but in the y direction, going perpendicular to this, it's concave down, right? And so you can kind of think that you have 2 kind of perpendicular parabolas to each other here, where one's going up and one's going down. And so in one way it's a max, and the other way it's a min. That's what we're talking about with a saddle point. Now that's not the only way that a saddle point can happen. So the other way that d can be less than 0 is that if this minus f of xy squared, if this is bigger than f of xx times f of yy, if this mixed partial squared dominates over fxx and fyy, then that also makes a saddle point. So just briefly, where is this d coming from? We're really deep down mathematically, it's coming from the determinant of this matrix of second order partials right here. So remember that f of xx and f of yx, that these are the same, right? And so when you have a 2 by 2 determinant, you do the diagonal going down, multiply those terms, and then you subtract off the diagonal going up. And so that's where this comes from. This matrix is what's called the Hessian. It tells us about curvature, but this is a curvature of a surface, not the curvature of just a one-dimensional curve. So that's kind of why it's a little bit more complicated, because you've got multiple dimensions to worry about. And so I think one good example to think about what can go on here is what if our function is just x times y. And so this has, you can double check this, going through the partials. This has a critical point at the origin, because its first order partial in terms of x is going to be y, and its first order partial in terms of y is going to just be x. And so y has to equal 0 from here, x has to equal 0 from there. So 0, 0 is the only critical point. What are the second order partials here? Well, f of x, so if I take y, take the partial in terms of x, I get 0. F of x, y, if I take the partial of x in terms of y, I'm going to get 1. And f of yx is going to be the same thing. Doesn't matter which one I choose. And if I do two partials in terms of y, well, then I'm taking x, derivative of x in terms of y, and that's also going to be 0. And so if you go through and do the determinant here, it'd be 0 times 0 minus 1 times 1. This gives us d is equal to minus 1. And so this is a case where these mixed partials are dominating over fxx and fyy. And if you wanted to think about what the graph of this looks like, what the graph of the surface looks like, well, on the x and y axes, this function is actually identically 0 on the two axes. And then the function goes up or down depending upon which quadrant you're in. So if you're in the first quadrant over the xy plane, it's positive, and then it'd be kind of negative in the second. Positive when x and y are both negative, and then negative the other side. And so you can kind of see this, you know, if you took circles around this and looked at what it plotted out, this is sort of the Pringle chip kind of graph, except it'd be kind of extending out. And so you can see this natural saddle here, except the saddle is skewed because on the x, it's no longer sort of on the x-axis going up and the y-axis going down. It's actually kind of turned 45 degrees from that. And so on the x and y axis, it's actually identically 0 all the way across, and it's along the line x equals y, where it's going to be the highest, and along y equals x is going to be the longest. So along x equals y is where you have this parabola going up, and along x equals minus y, that's where you have the parabola going down. Okay, so let's finish up this video going back to this example and using the second derivative test to identify the critical points that we saw before. So if f of x, so here's the same f of x before, same critical points, and we have our first partials here. So let's figure out our second order partials. So f of xx is going to be 6x. F of xy, if I take x and take the partial in terms of y, I'm going to get minus 4. So f of yx, or f of xy, is still going to be minus 4. And then two partials in terms of y is going to give me 6. Okay. So what is d going to be at 0, 0? Well, if I plug 0 in for x, this is the only variable I have in here. It's going to be 0 minus 4 squared, which gives me minus 16. So this is less than 0, and so we have a saddle point. Okay. For the other point, 8, 9, 16 27ths, if we plug this in, so we're going to get 6 times 8 ninths times 6, again subtracting off 16, same as before, but now over here on the other side, this is going to be, so that's going to turn into 2 over 3, and so I'm going to have 16, that's going to turn into a 2, so 16 times 2 minus 16, which is 32, which is definitely bigger than 0. And my partial in terms of x is positive at this point. And so then this is saying that 8, 9, 1627. Both of these partials are, both of the fxx and fyy are both positive there. And so this is a local min. One last note. So in all of these, we're assuming we're going on the assumption that d was either positive or negative. What happens if d is equal to 0? Well, if d is equal to 0, we don't get any information from the test. And that's the same thing that happens if the second derivative equals 0 in the second derivative test from Calc 1. And so you're not able to tell just from this test, and you'd have to do something else, which in our case, pretty much the only thing we'd have to be able to do is to very carefully graph it and look at it. So that is all for local maxes and mins. I will see you again soon.